In this video, we are going to introduce discrete Fourier series. This is our overview slide, which contains the topics that will be covered in this video. We'll spend about 5 minutes on the overview before going over each topic in more detail and with examples. First, we use discrete Fourier series when we use a computer to perform our Fourier analysis. To use a computer, integrals must be replaced by discrete sums, and all summations must be taken over a finite number of terms. So we're going to look at a simplified version of the fast Fourier transform, which can be used by a computer. We start with our continuous Fourier series. So these are the formulas we had from our previous video, and then we are going to use them to derive formulas for a discrete series. So here is my continuous, which is also rewritten here, but then this continuous function gets replaced with a discrete function that goes over a summation, and this integral here for our continuous function for Cn also gets replaced by a discrete function that is a summation. The next thing we'll look at is a matrix equation of the form of these discrete equations. We'll discuss aliasing, which says the sampling theorem says in order to accurately portray a signal by sampling, you must sample at least twice the highest frequency present in the signal. And we'll very briefly touch on positive and negative frequencies, which says that the normal Fourier series contains terms for both positive and negative frequencies. And when we develop in this video formulas for a discrete series, we did our range from 0 to 2n minus 1. But we really could have started at any arbitrary point. We didn't have to start at 0. We could have started at n0, and then instead of going to 2n minus 1, we would go to 2n minus 1 plus n0. And that will change our formulas for f of k as well as our matrices over here. And that covers our overview. So we'll start back up here with a little more of an introduction. And kind of the introductory idea before the advent of the modern digital era, electron spectra were obtained using analog spectral analyzers, which used an array of narrow band analog filters to split incoming signals into different frequency band. But now what we do is we obtain spectra digitally by recording the incoming signal with the discrete time intervals, or at discrete time intervals. As you know, when you do digital, you're sampling, so the time intervals, and they're discrete. And then we use an algorithm called the fast Fourier transform, the FFT. But when we use a computer to process this FFT, our integrals must be replaced by discrete sums because our computer isn't going to have a formula for the waveform. It's just going to have a bunch of samples. So we're going to be, instead of integrating a function, we're just going to be summing up a bunch of sums, and then all the summations must be taken over a finite number of terms. None of this negative infinity to infinity thing to go with our computers because it would just keep going and never terminate. So we're going to look at a simplified version of the FFT, which adjusts our previous methods to replace these integrals with sums and also make sure we're summing over a finite number of terms. So here again, I have my formulas that were from continuous, and we want the analogous discrete series equations. We're going to be looking at this waveform here. You can see it's periodic, or at least I tried to draw it as periodic, and this is the analog signal. And what we're going to do to get the discrete signal is we're going to sample 2n. I don't know why they just don't say n is equal to 8 times, but it's 2n is equal to 8. So n is equal to 4, but we're sampling 8 times. So here, over one period, t naught, we're going to sample 8 times starting at our first sample is going to be called t0. And since we're going 8 times and we're starting at 0, we're going to go up to t7. So we're sampling at t naught, T1, T2, T3, T4, T5, T6, T7. Again, 8 samples in our period. Then when we sample at time T naught, this is the value we get. When we sample at T1, we get this blue dot as our value. At T2, we get this blue dot. At T3, we have this blue dot. So our function just becomes this little trail of 7 dots. And here, just for illustration purposes, this blue dot is F6. That's our sample at time t equals 6. Again, our first sample is taken at t naught, and the first sample is called F0. Our last sample, F7, that's this blue dot, is taken at time t equals 2n, which is 8 minus 1 at t7. And looking at the steps outlined in your book, so step 1 is to determine the period of the signal, which we can see this is t naught. Step 2, the computer takes 2n samples of f of t spread evenly over the period. So here we said n is equal to 4, so it's taking 8 samples, and they're spread evenly over this period. And this t8, that would be the beginning of the next cycle. So also we've covered the whole period with this. And we're going to generate values f of k. So here we have f of 0, f of 1, f of 2, f of 3, 4, 5, 6, 7, which is equal to f of t of k. And t of k is equal to t naught divided by 2n times k. To give myself some space, I cleared out some things, but I left my Fourier continuous equations here, my Fourier discrete equations that we're deriving now. I have just notes on their 2n samples, and then here is my graph and the 2 steps that I need to take. Our new Fourier equations for our discrete version of our function that we'll use with the computer should generate the sampled value f of k. So we're not trying to derive the entire f of t, but our sampled values, f of k, from a new set of coefficients, c sub n, via some kind of sum. So an analogous equation to the continuous is we're getting our sample, our kth sample, and we're getting it from a sum from an integer n equals 0 to some maximum integer value, c sub n, this coefficient, e to the I omega n times t sub k. And this is just the time value, but now instead of a continuous time value, we have our discrete sets of time. And I'll just note that here. N is an integer, it'll run from 0 to some upper limit max. The continuous real variable t has been replaced by t sub k, the set of discretely sampled times. For Cn, we're going to use the following orthogonality condition, which I will not derive, but you'll look at it, and it's so similar to what we had for the continuous Fouriers, right? These are sines and cosines, so they're orthogonal unless your frequencies are equal. So when we're summing from k equals 0 to 2n minus 1, over here we chose 2n minus 1 because we're summing to the end of the period when we're sampling 2n times. And e to the I omega n tk multiplied by e to the minus I omega m tk, well, it's going to 0 unless n and m are equal. In other words, they're the same frequency. So we have our Kronecker delta mn times 2n. So again, same format. This Kronecker delta is here, giving us the same format for orthogonality condition. And the next thing we're going to do now is look at our proposed form of our sum. F of k is equal to n equals 0 to some maximum value, Cn, e to the I omega n t sub k. Do you remember when we did the continuous Fourier series and we said we wanted f of t to be equal to some coefficient times a sine and cosine? And then to find the coefficient, we multiplied both sides of the equation by the e to the whatever frequency we wanted. That's exactly what we're going to do here. So to find the coefficient for a particular frequency, we're going to multiply both sides by that frequency. So here I have multiplied the left-hand side of the equation here by the summation of e to the I omega m t sub k. Of course, then I have to do the same thing to the right-hand side. So here's my right-hand side, and I multiply by the same summation, e to the I omega m t sub k. The next thing I look at is I look at these e sub i's. So the thing about getting the coefficient is we used the orthogonality condition. So that here I have e to the I omega m t sub k. Here I have e to the I omega n t sub k. As long as omega m is not equal to omega n, it's going to go to 0. And here we have the particular, and in particular, we're going to use the Kronecker delta mn times 2n. To use this particular condition, I want to move my e to the I omega m t to the k next to multiplied by e to the I omega n t to the k, but I can do that. So I first pull out my c to the n summation, and then I have my k equals 0 to 2n minus 1 e to the I omega n t to the k e to the minus I omega m t to the k. And this summation, these two summations, this is kind of like an inner summation, so we're still summing over all these n's. That was my alarm, by the way, probably not yours. Now by orthogonality, I'm going to keep the left-hand side of my equation here, and over here, all of this is going to become our Kronecker delta times 2n. So I'm going to have my summation n equals 0 to 2n minus 1 cn times my Kronecker delta 2n, which implies my coefficients cm is equal to 1 over 2n for summation k equals 0 to 2n minus 1 f of k e to the I omega m t sub k. So that is the formula that I have over here. Now is a good time for an example. We're going to find the exponential form of the discrete Fourier series representation of x of n shown below. You can see this is a sampling of what looks like a triangle wave, right? Goes up, and a triangle form comes down, triangle form. Anyway, and you can see it's periodic. This is going to be our period here. We're at t0, we're at 0, t1, we're at 1, t2, we're at 2, and t3, we're at 3. And then we come back down for the next period. At t4, we're at 0. I moved my graph over here to make some room, and I made some notes. My period is equal to 4, right? 0, 1, 2, 3. So it's a period of 4. My omega n is 2 pi n over 4, so I'm going to get 2 pi n. There are 4 samples, which means that our capital N is equal to 2. Our omega naught now, I'm just plugging into this formula, is 0. Omega 1 is pi over 2. Omega 2, plugging in n equals 2 gives me pi. Omega 3, plugging n equals 3 in here gives me 3 pi over 2. And now I'm ready to calculate c sub 0, right? There's only 4 coefficients, so we're going to do them. So c naught is equal to, according to my formula up here, 1 over 2n, n is equal to 2, so 1 over 2 times 2, summation from k equals 0 to 2n minus 1, so that's 3, f of k e to the minus I omega 0, because n is equal to 0, t sub k. So now I have 1/4, and then for k equals 0 to 3, so I'll start with k equals 0, I have f0 e to the, now because we're at our t sub 0 is just time equals 0, so that's e to the 0, plus now k equals 1, f of 1, so I have t sub 1, so which is just 1, I have minus I, and omega naught is 0, so actually this e to the, this exponent is just going to be e to the 0, plus now k equals 2, f2, so I plug in t2, what is the time at t2 is just 2, and then I'm going to have e to the minus I omega naught, omega naught is still 0, so I'm just going to keep getting e to the 0. So I have 1/4 times my f naught times e to the, f naught is 0. Then I have f1, which is 1, f2 times 1, which is 2, and f3 times 1, which is 3. So my final answer is 3/2. Now I can calculate C1. I have 1 over 4. K goes from 0 to 3, f of k, e to the minus, now omega 1, when n is equal to 1, is pi over 2. So I'm going to have minus pi over 2I times my time sub k. So that's 1/4 f0 e to the 0 plus f1. Now t1 is equal to 1, so I'm left with e to the minus pi over 2I plus, for k equals 2, I have f2, my time, my second time interval is at t equals 2, so that's going to leave me minus pi I plus f3 for k equals 3, f3 e to the, and now I have minus 3 pi I over 2. So I have 1/4, my f0 is 0, my f1 is 1, e to the minus pi over 2I. So here I have my unit circle. I go in the clockwise direction because it's negative, so it's not increasing radians, but this other direction, clockwise. Pi over 2, that puts me at negative I. So that's this one here. So that's 1, that's f1, times my negative I. My f2 is 2, and then I have e to the minus pi I. Again, if I go over pi radians, I'm at minus 1. So that's this minus 1 here. I have f3 is equal to 3, and now I have minus 3 pi over 2. So minus 3 pi over 2 brings me back up here in the counterclockwise direction, and so that gives me an I. So what I have is 1/4, 0, minus I, minus 2, plus 3I, which is 1/4 minus 2 plus 2I. I have my calculation for C2 is equal to 1/4, k equals 0 to 3, f of k e to the minus, now omega 2, right, because we're at 2, is equal to pi, so minus pi I t to the k. So 1/4 f naught e to the 0 plus f1 e to the, now t is equal to 1, so minus pi I plus f2. When t is equal to 2, we get minus 2 pi I, and plus f3, and when t is equal to 3, then we get e to the minus 3 pi I, which is 1/4. This becomes 0. Our f1 is 1. Our e to the minus pi I gives us minus 1. Our 2 for f2, e to the minus 2 pi I, well, that just brings us all the way around. We get 1. Our f3 is 3, and e to the minus 3 pi I, so here we go around 2 pi, another pi gives us 3 pi I, so we're at negative 1. So our final answer will be minus 1/2. I'm just going to note that my C naught then is 3/2 here. My C1 is 1/4 minus 2 plus 2I from over here. And then my C2 is minus 1/2. That way I can make room for my C3 calculation, which I have here. Again, 1/4, k equals 0 to 3, f of k e to the minus, and now in this case C3, so we're looking for W3, minus 3 pi over 2I times our time. So 1/4 f naught e to the 0 plus f1 e to the, and now time of 1, minus 3 pi over 2I plus f2 times 2 times this is going to give us minus 3 pi I plus f3, and then times 3, that's going to give us minus 9 pi over 2I. So here we have f0 is 0, f1 is 1, e to the minus 3 pi over 2. So that's 3/2 pi in the clockwise direction. So here's 1, oh, I'm sorry, yeah. Here's 1/2, 2/2, 3/2. So that puts us at I. f2 is 2, e to the minus 3 pi I. So here's in the clockwise direction, here's pi, here's 2 pi, 3 pi, gets us at negative 1. And then f3 is 3 times e to the minus 9/2 pi. So we're going to do 9/2. So this is 1/2, 2/2, 3/2, 4/2, 5/2, 6/2, 7/2, 8/2, 9/2. That puts us at minus I. So our final answer is 1/4 minus 2 minus 2I. I'm going to make note of all my coefficients here, and I'm going to move them to the top here. So technically I'm done, because if you remember when we were doing the continuous Fourier series, we had these sine cosines, these e to the I omega t, these different frequencies, and then the problem was to find the coefficients. Essentially that's the same thing we've done here. Now we have a function f of k for discrete values. Now we can plug in other values of k, and we have the summation of the coefficients, which we've just determined, times our different frequencies. But although I say I'm done, I'm just going to demonstrate a couple of things and then write this final formula out for you. The idea is now that we have these coefficients, we can calculate our f of k, which I'm going to move the formula down here. And then I'm going to calculate f of 1 according to my formula. Of course, we know what the answer is because it's equal to 1. It's right here on our graph. But we're just going to verify that we can get that answer. And then later, the idea is that later you can plug in other k's like 5, 6, 7, 8, 9, or even negatives. Actually, you know what? I'm going to do both f of k equals 0 and f of 1. So let me change this to f of 0 for now. So f of 0, that is k equals 0, we're going to plug this in. That's going to give us, for n equals 0 to 3, so for n equals 0, we're going to have c0, and then e, since our t of k, our time at k equals 0 is 0, that's just going to be equal to 0. Then for n equals 1, I'm going to have c1. Again, I'm going to have e to the 0 plus now c2 e to the 0 plus c3 e to the 0. So I'm just going to get, since e to the 0 is 1, all of my coefficients summed together. And it actually ends up equaling 0, which is good because that's what our f of 0 is. Now I'm going to do f of 1. It's a little more interesting when k is equal to 1. So I'm going to sum from n equals 0 to 3. So just remember, k here is equal to 1, and it's the n, that these two n's that are changing. So when n is equal to 0, I have c0 e to the I omega n, which is 0, and then t sub k, t sub 1 is just equal to 1, plus then k equals 1, I'm sorry, n equals 1, so c1 e to the I omega 1, and again tk, t1 is just equal to 1, plus now n equals 2, c2 e to the I omega 2, again t1 is just equal to 1, plus for n equals 3, c3 e to the I omega 3, and tk is just equal to 1. Now I'm going to go ahead and plug in my constants and also my omegas, because I calculated those up here. So my constant, my first constant is 3/2, and this is e to the I omega 0. I omega 0 is equal to 0, so that's e to the 0. My c1 constant is 1/4 minus 2 plus 2i. E to the omega 1 is pi over 2, pi over 2i. Plus my c2 constant is minus 1/2. You'll see why I put the minus here, I hope. E to the I omega 2, which is just pi, so e to the pi I. So maybe this needs to be a minus sign. So let's look at that later. Plus our c3 is 1/4 minus 2 minus 2i e to the omega 3, which is 3 pi over 2i. To help me evaluate these exponents, I drew my unit circle. Like, I use this all the time. People are probably wondering why I'm always drawing circles, because certainly by now I know what a circle looks like. But anyway, here's pi over 2 radians, 3 pi over 2. So e to the 0, that's just 1, so I have my 3/2. I went ahead and multiplied the 1/4 in, so minus 1/2 plus 1/2 I, and then e to the pi over 2. So pi over 2 radians puts me at I, so this is I. And then I have my 1/2, and then the pi I, that's minus 1, so that's going to give me, this should be probably a plus, because I said this was a minus. I'm going to look at that again. Plus my 1/4, this will give me, I multiplied it in, so I have my minus 1/2 minus 1/2 I, e to the 3 pi over 2, that gives me a negative I. Okay, I fixed this. This should be a negative sign here because it's c2 is equal to 1/2, and that makes this a positive. Since e to the pi I is negative, I get a positive 1/2. So then when I add up all my constants and my i's, what I end up with is 1, which is exactly what I should have gotten for f1. So again, the fact that I calculated f1 isn't stunning because we already knew f1, but I just wanted to verify that my formula works, and now you can plug in different k's. And I should mention one of the points, it's not just calculating new f of 5 or anything. It's the fact that now you can do spectral analysis. You can look at the different frequencies and see the weights, like how much each frequency contributes to your f of k. Remember when I told you essentially after we did the coefficients that we were done? Some teachers like you to plug this back into your formula for f of k, so that's what we're going to do here. We're going to run the summation from n equals 0 to 3. For n equals 0, we're going to get 3/2. You can kind of plug that in and verify for yourself. For n equals 1, we're going to get our c1 coefficient, which I went ahead and multiplied the 1/4 in, So I have my minus 1/2 plus 1/2 I. Now e to the I omega 1, right, n is equal to 1, is pi over 2 times t sub k. In this example, t sub k is just equal to k, so I plug in my k. Now I need my, for n equals 2 term, my c2 is minus 1/2. My e to the I, my omega 2 is equal to pi. And again, in this example, t sub k is equal to k. Plus for n equals 3, I have my c3 coefficient, e to the I. This is omega 3, which is 3 pi over 2. And then t sub k is equal to k. And I kept repeating in this example, t sub k is equal to k. But that will not always be the case. So for example, if we had divided the interval originally into 8 samples, so here I divided this period into 8 samples, right? This is 1, 2, 3, 4, 5, 6, 7, 8 samples. Then t sub 0 would have been 0 still, but t sub 1 would have been 1/2. It would have been at the 1/2 mark. And t sub 2 would have been at 1. T sub 3 would have been at the 3/2 marks. So you have to be careful. And not every example, t sub k is not always equal to k. But we'll do, after we do our matrix example, we'll do another example where t sub k is not equal to k. Next, we're going to look at a matrix form of the equation for f of k and c of n. I'm not going to derive these matrix equations for you, but I'm going to tell you it shouldn't come as a surprise that there's a matrix form because one, you can see how the Cn, like you keep multiplying the f of 1, f of 0, f of 1, f of 2, f of 3, and for each calculation of Cn, like here's f0, f1, f2, f3, f0, f1, f2, f3. So that's where this comes in. And then you have this matrix here, which is defined by e to the I pi over capital N and k. And you probably noticed you kept calculating the same e to the I. Here negative pi I, here it's negative pi I. Here we have negative 3 pi over 2, which I thought we calculated before. But some of these things keep coming back. And so we can definitely look for the pattern if you'd like, and you can find the matrix. But I'm just going to say, let's take the matrix equations as they are without proof. I have our matrix equation here, and I have the example we just did, but now we're going to use these formulas with this example. And I kept the fact that T naught, the period's equal to 4, our omega n, we calculated already as pi over 2n. There are 4 samples, so n is equal to 2. I kept our omega 1, omega naught, omega 1, omega 2, omega 3 for whatever reason. Then I noted my values of k. So we're going to have k equals 0, 1, 2, and 3. So our t sub k, again, as we just discussed, it actually happens to equal to k, which is not always the case, but in this example it is. So t sub k is 0, 1, 2, 3. And our f of k, so f also happens to equal to k, but it's, the height. So 0, 1, 2, and 3. I moved our table over here. We probably will use it for reference. And then I moved my formula for my matrix, and I'm always going to use this last formula. So m of nk is equal to e to the I. Pi, in this case, our n, our capital N, is equal to 2 times our lowercase n and then k. So when I calculate m of 0, 0, and I plug that into here, so n is equal to 0, k is equal to 0, then this is going to become 0, and I'm going to get e to the 0, which is 1. Actually, anything that has a 0 in it, right, is going to be equal to 1. So that takes care of all of this. So now let's look at M11, first row, although it's not the first row. This is the 0th row. So the first row and the first column. Again, this is the 0th column. First row, first column. M11. So that's e to the I 2 pi n times k. So 1 times 1 is just 1. So I'm going to get e to the I pi over 2. M12 is equal to e to the I pi over 2. N is equal to 1. K is equal to 2. So that's 2 So that's going to give me e to the I pi. M of 1, 3. Again, n is equal to 1. K is equal to 3 in this case. So that's going to give me e to the I 3 pi over 2. And 2, 1. So n is equal to 2. K is equal to 1. That's when we multiply that together, it gives us 2. So we're going to get e to the I pi. M2, 2. When we multiply them together, that's going to equal to 4. So I'm going to get e to the I 2 pi. M2, 3. When we multiply them together, that gives us 6. So that's going to give me e to the I 3 pi. M3, 1. When we multiply that together, that gives us a 3. So that'll give us e 3 pi I. M2, 3. Again, that gives us a 6. So we'll have e to the I 3 pi. And M3, 3. That gives us e to the I 9 pi over 2. To simplify my exponents, again, I have my unit circle here. These are all ones, that's nice. E to the I pi over 2 is equal to I. E to the I pi coming over here, that's negative 1. M to the 3 pi over 2, that's down here, that's negative I. E to the I pi is negative 1. E to the I 2 pi comes all the way around to 1. E to the I 3 pi, we did that already, right? We come all the way around once, we go around another pi, that gives us negative 1. M to the 3 pi over 2, I think we did that, that's negative I. M to the I 3 pi, again we come around 2 pi, another 3 pi, that gives us negative 1. M to the I 9 pi over 2, so that's 9 quarters, so that, 9 halves. So here we have 1, 2, 3, 4, 5, 6, 7, 8. By the time we come around another 9 halves, we're at I. So this is my matrix, M of nk. I am going to kind of reduce that matrix here. So now I can start calculating the other thing I need. Since I have my matrix, I need my coefficients. And according to my formula, my coefficient is 1 over 2n. So in this case, n is equal to 2, so 1/4. The complex conjugate of m, so over here, all my I terms I'm going to negate. So I have my real terms are good, but here I have to negate this I. This is good, negate this I. This is good, this is good, this is good. Oh, this I need to negate, and this I need to negate. So this is m complex conjugate. And then I need to multiply by my f of k. So those are just, we actually just wrote that here. So 0, 1, 2, and 3 again. This is our f of k. Oops. I do my matrix multiplication. Remember, it's row times column. So 1 times 0 is 0. 1 times 1, that's 1. Plus 2 plus 3, that gives me 6. This next row times this column. This is 1 minus 2i minus, oops, no, that's 0, sorry. Minus I minus 2 plus 3i, that gives us minus 2 plus 2i. Multiplying this row times this column, that's 0. This is minus 1, 2, minus 3, that gives us minus 2. This row times this column, 0, I, minus 2, minus 3i, that gives us minus 2, minus 2i, multiplied by my 1/4 over here, and I get my matrix for C is 3 halves, minus 1/2 plus 1/2 I, minus 1/2, and minus 1/2 minus 1/2 I. And if you compare that to when we previously worked this problem using these formulas here, you'll see that our coefficients agree. So I'm going to leave this solution after we found the coefficients. Again, you can certainly then plug into your f of k, well, actually your f of k matrix. You could actually probably leave it in this form, or you can go back and do it in the other form we did for the previous example. Your book has another example of this matrix equation, which is f of t equals cosine t sampled 4 times over its period. If we graph this, this will give us this lovely picture. Here I have my cosine of t, and then it's sampled over 4 times over its period. I chose from here to be the period I'm representing. And starting at t naught, I need to divide it into 4. Remember, this is where it repeats, so we're going to stop here. So we have t naught is at 0, T1 is at pi over 2, T2 is at pi, T3 is at 3 pi over 2. And these blue dots above represents my sampled value. So at T0, we're at 1, at T1, we're at 0, at T2, we're at -1, and at T3, we're at 0. As we had done for our other example, I made some notes. Our n is equal to 2 because there's 4 samples. And then omega n, if I plug it into my omega n formula, since the period is 2 pi, is simply equal to n. Then I made this table, so k, since it's sampled over 4 times, k is going to be equal to 0, 1, 2, and 3, 4 values for k, starting at 0. My t sub k, as I mentioned, it's no longer equal to k, it's equal to 0, pi over 2, pi, and 3 pi over 2, as we have over here in this drawing. And our f of k, which we just read off of our drawing, is 1, 0, -1, 0. And now I'm ready to use my formula for the matrix nk, and I always use this formula here. So again, if we have a 0, so if we're at the 0th row or 0th column, because of this n is equal to 0, and actually the k is equal to 0, well, either one. If either one's equal to 0, this is e to the 0, which gives us 1. So that's here. So let's start with E11. So when we multiply n times k, we get 1. So we're left with e to the I pi over 2. M12, when we multiply n times k, then we get 2. So we get e to the I pi. M13, so we have e to the I 3 pi over 2. M21, multiply them together, you get 2. It cancels, you get e to the I pi. M22, you multiply them together here, you get 4. So this becomes e to the I 2 pi. M23, multiply these two together because that's what it says to do over here, you get 6. So when you have 6, this becomes e to the I 3 pi. M to the 3, 1, you multiply them together, you get 3, e to the I 3 pi over 2. M to the 3, 2, again this is 6, so you get e to the I 3 pi. And M3, 3, that gives you a 9, e to the I 9 pi over 2. And then I put my unit circle, my row and my column are set. E to the I pi over 2, we're at I. E to the I pi, we've come over here to -1. E to the 3 pi over 2, we're down here, we're at -I. E to the I pi, again, we're at -1. E to the I 2 pi, we've come all the way around to 1. E to the I 3 pi, we go all the way to 2 pi, and then come back around to pi, and we're at -1. M to the 3 pi over 2, again, that's -I. M to the 3 pi, again, we come around pi radians, 2 pi radians brings us back, and then 3 pi radians gives us back to -1, and M33, 9 halves, so we go 1 half, we're here at I, 2 halves, we're at pi, 3 halves, we're at -I, 4 halves, we're back at pi, 5, 6, 7, 8, 9, so by 9 we're back at I. Now we can calculate our Cn. And the formula over here is 1 over 2n, complex conjugate of m, f of k. So n is equal to 2, so we have 1/4. Complex conjugate, it's this matrix M, except we negate all the complex terms, which is just, this becomes a -I, this becomes an I, this becomes a -I, this becomes positive, and this becomes negative. And we multiply by f of k, which we have over here. 1, 0, -1, 0. So when we do the matrix multiplication, our final coefficient matrix is 0, 1/2, 0, 1/2. Now plugging in our coefficients into our formula for f of k, and our formula for f of k is up here at the top when we first talked about discrete Fourier systems and we have our formulas. So the formula is summation n equals 0 to 3, c sub n, e to the I, omega n, tk. The first thing is omega n. We said that's just equal to n because omega n is 2 pi n over the period. So I plugged in n for omega n. And then the next thing, and this was totally optional. It looks like it's optional in your book, but this is what I would do. T sub k, I found the formula for T sub k, it looks like it's pi over 2 times k. So I substituted that in. Now going through the summation, n equals 0, C0 is equal to 0. So this whole thing is 0. For n equals 1, I get my coefficient is 1/2. E to the I, again, n is equal to 1, so that's 1 times pi over 2k. This is n equals 0, n equals 1, n equals 2. Our C2 coefficient is 0, and our C3 coefficient is 1/2. E to the I, and then 3 times pi over 2k. So this is our formula for f of k. And if you actually try to recreate it, it's actually a pretty bad formula. And that's because we don't have many samples, right? To estimate a cosine with 0 and 1 and -1 is pretty weak because there's so many values in between. So the fact that this is a poor sample is because we were doing this by hand. So we only wanted 4 samples, but really if you wanted to sample a cosine, you would take way more samples. Here we're going to look at the spectral plot of Wn, which is equal to n, and we're going to plot our coefficients. So for n equals 0, W0, our coefficient is 0. For n equals 1, our coefficient is 1/2. For n equals 2, our coefficient is 0. And for n equals 3, our coefficient is 1/2. Before I talk more about this, I'm going to remind you about the connection of these c sub n's and our sines and cosines. Remember when we started with Fourier series, we started Fourier series in terms of sines and cosines, and then we went to these exponential forms here. But we also went from our sines and cosines. We used this formula that we derived from Euler's identity, and then we solved for our Cn, which is for our exponential form, in terms of our Am and our Bm, which was our trigonometric forms, our sines and cosines. So the thing I want to remind you is when we have these coefficients for e to the I omega n, this relates to a sine or cosine of omega n t. And here we would say t sub k because we're talking about the discrete times, whereas here we would just say t because we're talking about the continuous time. So from that, I'm just going to remind you that these omega n's here in our formula for f of our discrete k function, they're related to these omega n's in our Fourier transform over here. And the Cn, it's not going to be equal to the An and Bn, but it's related, and it's relating these same frequencies. And what I want to do is look at this spectral plot. So here when n is equal to 0, when we're talking about W0, and the frequency is equal to 0 because we found that Wn is equal to n, then we're looking at some coefficient An cosine of omega n is 0 times t, which is just 0. So this is some an, some sort of constant function, and we expect the constant function not to really have any role in a cosine function. In other words, the cosine doesn't have a sign of, doesn't have a component of just a straight line. When n is equal to 1, our omega 1 is equal to 1. So we're looking at some coefficient a1 cosine of omega t is just cosine of t. And this we expect something non-zero, something close to 1, right? Because the function we're trying to model is cosine t. So we expect something non-zero, which we have right over here. We have 1/2. Then n equals 2, omega 2 is equal to 2. So we have some coefficient a2 times cosine of 2t. Again, that's omega t. And this we expect to be 0 because there's we're modeling a pure cosine of t frequency, so we expect nothing of cosine 2t, and that's why this is 0, which is what we have. For n equals 3, then we're looking at a coefficient cosine 3t, so again we expect a 0 because we're modeling a pure cosine t. So we expect 0, but we get this other value of 1/2. And your book makes this note: the parts of the spectrum make sense and other parts do not. The fact that C0 and C2 are 0, that's the part that was just some line, and C2 was frequency 2t. So we expect those to be 0, and C1 was non-zero, which is exactly what we expect because this is a cosine t function we're modeling. But the component at omega 3 equals 3 makes no sense because there's obviously no cosine 3t component of our cosine t function. So this suspicious extra component is referred to as an alias. And the alias arises from the fact when we had our 4 sampling points, the two functions cosine t and cosine 3t give exactly the same values. So over here, cosine of t and cosine of 3t both have the same value of 0. So we can remove the alias by sampling more times per period. So if cosine t is sampled 8 times, for example, instead of 4, the new spectrum appears as shown here. And you can see that we removed that alias at 3. However, now we have an alias at 7, which occurs because cosine 7t and cosine t have the same value at the sampling points. They're both at 0. So we have a sampling theorem that says in order to accurately portray a signal by sampling, you must sample at least twice the highest frequency present in the signal. So I have this start. If this is done with a discrete Fourier series, the resulting spectrum can be trusted to have no aliasing up to half the sampling frequency. Therefore, here, when we have our 8 samples, the spectrum is valid up to W4 because we want to sample twice the highest frequency. So we half it to see where it's, so you basically need to double your frequency and then you're good for half of it, half the space. The signal f of t equals cosine plus cosine 3t has period t naught equals 2 times pi and must be sampled at a frequency 6 times over the interval in order to trust the spectrum up to omega n equals 3. And actually at this point we had gone straight from the matrix equation topic into aliasing. So the important thing is we have the sampling theorem that says in order to accurately portray a signal by sampling, you must sample at least twice the highest frequency present in the signal. The last topic in your book, which we're not going to spend a lot of time on, is positive and negative frequencies. So the normal exponential Fourier series contains terms for both positive and negative frequencies. And when we developed the discrete form of the series, we created a spectrum that ranged from 0 to 2n minus 1. And this discrete series analysis can be set up with all the sum over n, starting at some arbitrary integer n naught instead of 0. And then we range to 2n minus 1 plus our n naught, which is over here. And then we would write our f of k this way, and our matrix equation would change to this. There's a couple of other points in your book that I'll let you look over. One being that there's another way of looking at aliasing through this lens, but I think this video is long enough, so I'm going to stop here. To review what we covered, when a computer is used to perform Fourier analysis, integrals must be replaced by discrete sums, and all summations must be taken over a finite number of terms. So we looked at a simplified version of the fast Fourier transform usable by a computer. Here we reviewed quickly our continuous Fourier series, and then we used this continuous Fourier series, whose formulas are here, and we converted them to formulas for a discrete series. We also looked at the matrix equation, so we converted this to a matrix form, which is also easier to do by computer. And then we talked about aliasing, and we said the sampling theorem says in order to accurately portray a signal by sampling, you must sample at least twice the highest frequency present in the signal. And we talked very briefly about the positive and negative frequencies, essentially that the Fourier series contains terms for both positive and negative frequencies. And when we developed for discrete series, in this video, we went from the range from 0 to 2n minus 1 to get our samples, except we really can start at an arbitrary integer n naught and then go from, instead of 0 to n naught, or we start at n naught instead of 0, and then we end at 2n minus 1 plus n naught instead of 2n minus 1. And that will change our discrete Fourier series formula to this form and our matrix form to this equation. And that's it for this video. Thank you for watching.